Presentation will be What Do Yellowballs Have to Do with the Birth of Stars by Dr. Grace Wolf Chase. Yellowballs, or YBs for short, were named by their discoverers, citizen scientists who identified them by their appearance in infrared images that were used by the Milky Way Project, one of the many people-powered research projects launched on the Zooniverse platform. YBs are links between the cold interstellar clouds that form stars and the types of stars that form. Tonight, she will show how her and her fellow colleagues are using a catalog of over 6,000 YBs across the Milky Way to examine the conditions under which different stars form, and she will showcase an activity they are developing that enables students in introductory astronomy classes to participate in this research while learning fundamental concepts in astronomy. Dr. Grace Wolf Chase is a senior scientist and senior education and communication specialist with the Planetary Science Institute, a nonprofit corporation that employs scientists and educators around the world. She conducts research on how stars form and shares her love of astronomy with diverse public audiences. She's published dozens of academic research papers as well as popular articles and has contributed chapters to several books on science and religion. Please welcome Dr. Grace Wolf Chase.
Thank you, Kurt. First of all, I am delighted to be back with you folks at the Naperville Astronomical Association again. And I am delighted that tonight I've got my spouse and son, Dennis the older, Dennis the younger, and Dennis the younger's girlfriend, Irina, as part of the audience here. So thank you guys for being here. When I submitted the title of this talk to Kurt, he asked me if this was the same presentation I gave in 2019. It's not, but it is about ongoing research with the same objects that I spoke of. That was right on the eve of the pandemic. Shortly into the pandemic in 2020, I sadly lost my position of 22 years at the Adler Planetarium and spent a couple of months kind of wondering, where do I go from here? Am I going to stay in astronomy or do something else? Well, in the summer of 2020, a wonderful opportunity came up with a terrific nonprofit organization known as the Planetary Science Institute. PSI has headquarters in Tucson and Boulder, but it employs scientists around the world. Now, it is a soft money institution, which means that the only salary scientists get is through grants that they pull in, and then the overhead from those grants goes into paying the full-time staff, the backbone of the organization, like IT, HR, and the people who manage the grants. So that was, I'm very, very pleased to be part of this terrific organization. At the time that I left the Adler, I also had a grant that had nothing to do with my research, but it was a grant from the Alfred P. Sloan Foundation, and the idea was to engage faith and interfaith communities in people-powered research through the Zooniverse platform. Now, there was one problem in transferring that grant to PSI. Since it was a grant from a foundation, foundations, as some of you may know, provide much lower overhead cost rates than government grants do. So I had to find a new home for my grant. And I wound up working with some folks that I've worked with for decades now at the AAAS DOSER program, DOSER standing for the Dialogue on Science, Ethics, and Religion. So the latter half of 2020 was spent with the logistics of transferring this grant, rebooting this project that I was working on that really had nothing to do with my research, and then starting to write research grants for PSI. So that's 2020. In 2021, I had a hip replaced, and the following year, I had 2 really long spinal surgeries that took me out of it for quite some time, had a very lengthy recuperation period. So now it's 2023, and this is sort of why I haven't spoken with you folks in 4 years now. And tonight I'm really happy to be talking about my ongoing research, primarily with my colleagues Charles Curtin, Associate Professor of Astronomy at Iowa State University, and Katie Devine, Professor of Physics at the College of Idaho. Over the years, we've also worked with some incredibly talented graduate and undergraduate students. So Let's start with just classifying stars. I'm sure many of you have seen a Hertzsprung-Russell or HR diagram before. This is one of the most useful tools in astronomy. It's a special type of what we call a color magnitude diagram. And it plots the luminosity of a star versus its temperature. Now, to calculate the luminosity, you need to know the distance. Luminosity is absolute brightness, not apparent brightness in the sky. And you will find that different types of stars fall in different parts of this diagram at different stages in their lifetimes. My first year in graduate school at the University of Arizona, an entire semester-long class was devoted to understanding, or at least trying to understand, the physics behind stellar evolution and how this works. So the main sequence is where stars of all masses spend when they're fusing hydrogen to helium deep within their cores. The sun will be stably on the main sequence for several more billion years. The path here that the sun will travel over the course of its lifetime, starting with pre-main sequence and winding up eventually as a white dwarf star. Now, along the main sequence, we talk about three different sort of general categories of stars. High mass stars are stars that have temperatures in this range here that's colorized dark blue. So O stars and what we call early B stars on the main sequence are massive stars more than 8 times as massive as our sun. Intermediate mass stars run from type A to B3, basically the part of the main sequence that's colorized light blue. And then low mass stars are stars under about twice as massive as the sun, and they range from the F stars down through the very abundant M stars. Now, what's really interesting is these high mass stars. They're very important because these are the stars that end their lives as supernovae, and they enrich space with the products of millions of years of building up heavy elements. They're also very rare. Less than about 0.1% of all stars are these massive stars. In fact, high mass stars plus intermediate mass stars, which range from about 2 to 8 times the mass of our sun, together are a little less than 1% of all the stars. On the other hand, the dinky little cool red stars make up about 76% of all the stars. And those of you who keep up with the searches for exoplanets, planets that orbit other stars, may know that most of the potentially habitable exoplanets that we know of right now orbit M-dwarf stars. Now, these are stars that you can see in visible light. But before the pre-main sequence, stars are sort of cocooned in clouds of dust and gas that block the light from those stars. So that before the pre-main sequence stage, you won't find them on the HR diagram because they're invisible. You need infrared and radio telescopes in order to observe them. So this is a special case, as I said, of a color magnitude diagram. We're going to be coming back to those a little bit later. There's another useful tool in astronomy called a color diagram. Now, these are 2 plots taken from the Sloan Digital Sky Survey, where you find that if you plot different stars, color versus color, where color means something different in astronomy than it means in the general vernacular. By color, I don't mean yellow, blue, mauve. I mean the difference in the amount of light that you measure coming from a star between one filter and another filter. So on these plots, we're plotting the difference in the amount of light coming in through ultraviolet, green, red, and infrared filters. And you find color is not only a very useful concept in astronomy, it's very useful because different spectral types of stars cluster in different regions of a diagram like this. And so you can figure out where, for example, a G5 star belongs, even if you don't know the distance to that star. So this is another type of diagram that's very, very useful in astronomy. Now this is the picture we have built up over time for how a low-mass star forms, a star less than 2 times as massive as the sun. This picture was built up through many different observations and on many different wavelength scales. And the top 3 stages depicted here are invisible. We can only observe them with radio and infrared telescopes. So stars start out they form from what we call dense cores that are part of larger molecular clouds in space. Now these dense cores dense is kind of a misnomer because the density in a dense core is still about 100 trillion times less dense than air. These objects are maybe about 1 trillion miles across, but they're the units that collapse into eventually forming stars and planetary systems over millions of years of time. Now, before a star is on the main sequence, it's known as a young stellar object, or a YSO. And as I said, these stages are invisible. Once we have an actual star and what we call a protoplanetary disk around the star, we call that a protostar. These are stars that are still accumulating most of their mass. And we call those objects protostars or class 0 or Roman numeral 1 objects. Don't ask, it's crazy, nomenclature in astronomy. When they're a little bit older and they've dispersed their envelopes, they're known as class 2 YSOs. And I'm telling you this because we also can classify YSOs on a color plot, only in the infrared. So the Spitzer Space Telescope was an infrared observatory that was launched in 2003. It exhausted its supply of liquid helium in 2009. Infrared telescopes have to be kept very cold because pretty much everything emits infrared light. We all are very bright at infrared wavelengths of about 10 microns. So the observatory actually operated for a while after it exhausted its liquid helium supply. Through early 2020, it could still operate at the shortest infrared wavelengths. And it performed many large surveys that were intended to be of useful to the entire astronomical community for many years. So in this diagram, what you're seeing is a color plot showing the difference in magnitude, pairs of infrared magnitudes now, and plotted on this plot are a class 1 protostars, which lie in a very different part of this diagram from slightly older stars of the class 2 variety. And then this cluster of objects that's marked photospheres down here, those are simply main sequence stars of all different kinds. So these color plots are very useful if you know a priori what type of an object you have, and you put it on a diagram like this, you can sort of place it in the evolutionary scheme of things. So that's the simple picture of low-mass star formation. High-mass star formation is a little more complicated. So what you're seeing here is a beautiful picture of the Whirlpool Nebula. I'm sure many of you recognize that, next to Orion. Orion is what we call an H2 region, an ionized hydrogen nebula around very, very bright young O stars. And the fuzzy red patches indicate what we call H-alpha emission, when electrons recombine with protons to form hydrogen atoms. There's a spectral line known as H-alpha that has this distinctive red glow. So in the Whirlpool Nebula, you can see these things stretched out along the spiral arms of this galaxy. I have a hard time pointing and talking at the same time here. You can see the patches, those fuzzy pink patches, are stretched out along otherwise very dark spiral arms, and the dark stuff, that's where stars actually start to form, in the dark, cold gas and dust that you can't see in visible light. So you get the big picture here in the Whirlpool Nebula, but the Orion Nebula is the closest region in our galaxy, the Milky Way, that's currently forming these very bright O-stars that are intrinsically more than 100,000 times as bright as our sun. So I think probably almost everyone here knows where the Orion Nebula is. This image goes back to 1995. I think I remember when I remember when I first showed this image to the NAA, but I wasn't here yet in 1995. So this is an image that was put together by the Hubble Space Telescope over 20 years ago. The nebula is lit up by the bright O-stars at the center, but when massive stars form, they form along with all types of stars. So there are also many fainter stars in this cluster, in this image. In fact, there are about 2,800 stars within about 20 light years. To give you some sense of how densely packed that is, today, the nearest star to our sun is a little over 4 light years away. But we have good reason to think that our solar system formed in an environment like this, where some of these massive stars exploded and enriched the forming solar system in some very, very heavy elements. So these processes, this is a very complicated region to understand. Gravity isn't the only important physics at work here. There are magnetic fields, radiation, turbulence. It's kind of messy, and these processes play out over enormous scales in both time and space. So let's look at another external galaxy again. This is the Phantom Galaxy, and I love this comparison of images. Going from left to right, you're looking at shorter wavelengths to longer wavelengths. So you've got the Hubble Space Telescope image of this galaxy, and then you have a combined Hubble image with the JWST, James Webb Space Telescope, that probably you all heard of, that observes the universe in what we call near and mid-infrared light. And then at the far right, the orange coloration was obtained with the Atacama Large Millimeter Array at millimeter wavelengths out towards the microwave part of the spectrum. So one of the things you'll notice are the infrared images of this galaxy look kind of like Swiss cheese. Well, that's what massive stars do over their lifetime. They create these bubbles and voids through winds and through radiation when they're young, like the stars in the Orion Nebula, to when they become supernovae and they sort of clear house. So this is very interesting because it shows you what you see in visible light versus all this individual stuff. These long, stringy filamentary networks, that's where stars first begin their lifetimes. So this is an image taken by the Herschel Space Observatory, which observed the universe in sort of the far infrared to submillimeter part of the spectrum. And the Hubble Space Observatory was specifically designed to study the universe at long wavelengths. It was critical in identifying what are now called hub filament systems that are recognized as the actual birthplaces of stars across the Milky Way. I'm showing you the image of Orion here. So where you see the light bluish coloring, that kind of outlines where the Orion Nebula is. But all of these wavelengths are well outside the human eye, visibility to the human eye. So these are all at very far infrared wavelengths. If you go to the Herschel site, you can pull up dozens of these things over the galaxy, showing these long, beautiful filamentary structures that are often connected at what we call hubs. Now, these filaments can be 100 parsecs long, multiplied by 3 to get that, approximately 3 to get that in light years, but only be about a parsec, a few light years in width. So these are like long strings. And this is where the birthplaces of these filaments are where stars begin their lifetimes. So back to the Spitzer Space Telescope that I mentioned earlier. The Spitzer Space Telescope did many large imaging surveys across our galaxy, and the view that you're seeing here is just that little boxed region on this visible light photo, where everything that's dark here towards the center of the galaxy is bright here in this image. This image is part of a much larger survey that covers about 300 square degrees of the Milky Way. And pretty much, I know you can't see it from the back of the room, but pretty much everything that's blue here is a little pinpoint star somewhere along the line of sight through our galaxy, stars of all kinds. Whereas the pink and green stuff highlight gas and dust in our galaxy that are particularly bright at these wavelengths. At 8 microns, for example, a lot of what you're seeing here, colorized green, is due to complex organic molecules in our galaxy. Organic molecules known as PAHs, for polycyclic aromatic hydrocarbons. So the massive young stars, like stars that are even younger than the stars that excite the Orion Nebula, produce features that look like this in the infrared in our galaxy. And of course, in our galaxy, there's so much gas and dust, we can't see all the H2 regions in our galaxy like you can when you look to like the Whirlpool galaxy. So back about 15 years ago, I had a conversation with the creator of Zooniverse that I know a lot of you are familiar with Zooniverse, about the possibility of creating a star formation zoo. The very first project launched on Zooniverse was called Galaxy Zoo. I'm sure some of you have actually participated in that and classified galaxies. So we brought together a group of star formation enthusiasts like myself and decided to create the Milky Way project, which was first launched on the Zooniverse platform in late 2010. Now, since it was only the 9th project ever launched, you may know that there have been hundreds of projects launched on Zooniverse to date. So the Milky Way project used these Spitzer images to enable citizen scientists to identify the infrared signatures of these H2 regions across a significant portion of the Milky Way. And as participants were searching for these so-called bubbles, they started using the hashtag Yellowball to chat about some different features on the images on the Milky Way project discussion board. All these projects come with discussion boards where volunteers can chat amongst themselves and with the scientists. So yellow balls are really interesting. One of their most intriguing features is this is the first stage in the formation of star clusters where you can actually link the properties of protostars within the yellow balls to the birth clouds that you see at these very long wavelengths where these stars are forming. So what you see depends on the wavelength that you're looking at. And in this case, at earlier stages, you can't distinguish protostars within these clouds. At later stages, the stars have blown away their birth clouds. So this is kind of a very important snapshot into forming into star clusters as they're forming. So in 2015, my colleagues and I published an initial look at these yellow balls or YBs, which we were able to link to many various different signposts of massive star formation. The volunteers had just kind of identified these on an ad hoc basis, and we were working with just some of the brightest yellow balls that are out there. And so we initially proposed this evolutionary sequence. The time scales you see here are very rough. They're based on models of how these regions are expected to evolve. And the labels here basically indicate what happens as a massive star starts to heat up its environment, the gas and dust around it. So first it forms what we call a photodissociation region. That's just a fancy set of terms to describe how molecules are dissociated around very young stars. Really massive stars then start to ionize their environments, and you wind up with an H2 region where there's a lot of ionized gas around, a lot of ionized hydrogen around these objects. So this is just sort of a little diagram that shows where you get this overlap of the dust and the gas. You get the yellow color in these images. So are yellow balls yellow? Not by any way we would think of the color yellow. They're not. Now what was interesting about this is that initially we thought we were seeing the evolution of a region like Orion. However, stars that are more modest, stars that are what we call intermediate mass stars, that are between about 2 or 3 and 8 times the mass of the sun, can, when they're very young, produce these photodissociation regions. So not every yellow ball necessarily evolves into something that looks like this. That made these stars even, or these yellow balls, even more interesting to us, because in principle, they can help us understand differences in the way these massive star-forming regions form and lower mass stars form. So we can identify different modes of star formation. So isolated low mass star formation proceeds like that little diagram I showed you, with the nice little dense cores collapsing through gravity and forming stars and planetary systems. That works for isolated objects less than about 2 solar masses. At the opposite end of things, you have these high mass star forming regions, which are really high stellar density clusters forming stars that include stars greater than 8 solar masses. And these are stars that can first photodissociate their gas and then evolve into these full-blown H2 regions. And the interesting thing is the intermediate mass star-forming regions may link these 2 modes of star formation. We still don't understand how high mass stars form very well. There are lots of different theories at this point, and they're not very well constrained. So we were pretty excited because the intermediate mass case may actually be the key to understanding the transition between these different modes of star formation. However, up until our project, there were only a few dozen examples of regions that were known and studied. So beginning around 2016, we specifically asked volunteers to identify these YBs in the Milky Way project. And by 2018, they'd identified the locations and marked the angular sizes of more than 6,000 of these across 300 square degrees of the Milky Way. So here's the sun. So we never see our galaxy like this, right? This is an illustration of the shape of our galaxy. The Milky Way project covered this wedge toward the inner galaxy, toward the galactic center and around it, and a couple more wedges in the outer galaxy. Now, when I last spoke to the NAA in 2019, we were in the process of analyzing the results of a pilot study of 20 square degree region that contained roughly 10%, a little less than 10%, maybe 8% of the entire database of these objects. We published those results in the Astrophysical Journal in 2021, and one of the very interesting results that we considered very interesting was that only about 30% of our yellow balls were actually associated with the formation of massive stars. If this result is characteristic of the entire surveyed region, the full survey will expand the number of known intermediate mass star-forming regions by nearly 2 orders of magnitude. So this is taken from a presentation by my colleague, Katie Devine, at a recent conference at Caltech, where you're looking at newly identified star-forming regions via these yellow balls in only 3 square degrees out of the entire surveyed region. So if you ask me, what are yellow balls? I would answer you, YBs are chimps. And if that's as clear as mud, a chimp is a compact, high and intermediate mass protocluster. This acronym hasn't caught on with my colleagues yet, but in a recent grant proposal, one of the reviewers told us that we should really, going forward, name these things something different from yellow balls. First of all, they're not yellow in any way, shape, or form that our eyes would perceive. And even if they were, how many things are yellow, right? Yellow is not very descriptive of what they actually are. So I'm suggesting a new descriptor, a new acronym to describe these objects here. Why is all of this important? Well, the reason this is important is because massive stars are critical to distributing the elements of life. And it's of great astrophysical interest to identify differences in the properties of environments that do and don't produce massive stars. Planetary systems that form in the proximity of massive stars, like the Orion Nebula, for instance, like where we think our solar system formed, may be very different from the properties of planetary systems that form around in clusters with more modest stars. So I'm going to take you through some of the ways we measure the properties of these YBs, including a way that you can actually help us with this research if you so desire. So our first step in studying these objects is doing photometry, that is, measuring the amount of light coming from YBs at different wavelengths. That gives us information on the color and the temperature of these objects. Now, if we also have distances, and I'll show you in a little bit how we actually find the distances to these objects, then we can calculate important physical properties like the actual size, not just the angular size on the sky, the mass, the true brightness or luminosity. And the luminosity gives us an upper limit to the most massive embedded star, which is really, really useful. So, doing photometry on a YB isn't like measuring the light from stars, because YBs are extended objects in complex backgrounds, since pretty much everything in the galaxy emits infrared light. We, and by we I mean primarily Katie and her fantastic undergraduate students, developed a Python-based interactive, semi-interactive tool that enables the user to measure the light or flux from YBs at different infrared wavelengths. The user selects points around the YB and the code interpolates over the area within those points to create a background estimate. The difference between the background and the image creates a YB-only image, calculates the flux of the YB. Photometry at 4 wavelengths takes about 1 minute per source, and we need multiple measurements of each source to basically estimate the errors in photometry. So, as you can imagine, for the number of these objects, this is a process that takes quite a while to do. Now, in our 2021 paper, we managed to get good photometry on about half of the 518 YBs. And what you're seeing, and this is why I was showing you all those color plots earlier, this is a color plot now at mid-infrared wavelengths, where we're not plotting difference in magnitude, difference in brightness. We're plotting the ratio of fluxes at different mid-infrared wavelengths. Now, the ratio of flux is equal to a difference in magnitude, right? The magnitude scale is a logarithmic scale. A star of magnitude 1 is 2.5 times approximately as bright as a star of magnitude 2. A star of magnitude 1 is 100 times brighter than a star of magnitude 6. So here we're plotting brightness ratios, not differences in magnitude. So one of the things that we noticed, the colors here and the shapes just indicate YBs that are linked with objects in other catalogs. But the important thing is, this rectangle up here are where you expect the colors of your average kind of compact H2 region to lie. And most of the newly discovered YBs lie in a different part of color space. So this is plotting the flux ratios at these wavelengths. We measured light at four different wavelengths. The histogram on the right here is plotting just one color, the flux ratio at an infrared wavelength of 12 microns divided by the flux ratio at 8 microns. And what this shows is that our YBs are much brighter at 8 microns than they are at 12 microns. This line here is the average ratio for an H2 region. This line here is the average ratio we had for the Yellowballs in 2015 that were the whoppingly bright ones. And this histogram here moves even further to the left. And this is exactly what we'd expect. Without going into all the nasty physics, this has to do with the compactness and the amount of emission coming from these polycyclic aromatic hydrocarbons at 8 microns. So we have these intriguing hints that colors can tell us a lot about YBs. But we didn't have a large enough sample, and doing reliable photometry is a really time-consuming process because we really need multiple measurements. You saw these things are kind of a mess. Everything emits infrared light in our galaxy. So we decided we needed some help, and we decided to ask for help in addition to our team. We received one of the first NASA Citizen Science Seed Funding Program grants to develop Periscope, which is a classroom activity that enables introductory astronomy students to assist the photometry while learning important astronomical concepts. And yes, I can take credit for this acronym. I love to come up with acronyms. People Enabling Research, a Yellowball survey of the colors of protostellar environments. So in this classroom activity, students learn about the importance of color magnitude and color diagrams in astronomy by using the tool we developed to conduct photometry at several different infrared wavelengths. They plot and they analyze their results on color diagrams and with histograms. And then they compare their results, the results that they get for the sample that they worked with, to the results that we presented 2 years ago. I can't emphasize this enough. This activity does not affect the students' grades in these classes in any way, shape, or form. And they choose whether they want to donate their results to our project. To do anything else would be unethical. You can't use students in introductory astronomy classes that way. This isn't like Zooniverse where volunteers know beforehand they're contributing to the research and they choose to do that. So this is totally on a students, would you like to incorporate this on your resume? Would you like possible acknowledgement on a paper and to be involved in any interviews that come out of press activity linked to this research? So we beta tested Periscope in classrooms at the College of Idaho, Iowa State University, and Willamette University, and we're currently in the process of using the results from that beta testing to improve our tool and to improve the activities. Now, one of the things I want to mention is that this tool could conceivably be used without the classroom-associated activities by individuals such as amateur astronomers. Hint, hint. I have a sign-up sheet here and some business cards where, if you'd like, you can leave your number and an email address. This does not commit you to anything. We're not yet ready for prime time. But if you think you might want to become involved in this research project for some kind of acknowledgement, I can't necessarily promise co-authorship on a paper, although that's not entirely off the table, but I can let you know when we are ready for prime time, because we really do need help with the photometry, with flagging sources and things like that. So anyway, that's something to keep in mind if you want to leave contact information at the end of this talk. Now, it is not necessary to have Python installed on your computer in order to use our tool. I use Spider, which is part of the Anaconda package, so I do have Python on my computer. But in classrooms, students use an online platform called Colab, which works with Jupyter notebooks that some of you who are familiar with Python might be familiar with those. So our landing page for Periscope is going to go live after we've addressed a few of the technical issues. We intend to publish the first data release of this catalog of YBs with fluxes and errors and associations and other catalogs and such by the summer of 2020. but we're also going to maintain an updatable online database where we can add new measurements and constrain the errors better as we go for subsequent data releases. The more measurements we can get, the better we can estimate those errors in measured fluxes, and the more reliable our results will be. So we recently, I'm happy to say, received an NSF grant for the next 2 years to analyze the entire YB database. So I promised you I would tell you something about how we calculate distances to YBs. Amateur astronomers know that there are many different ways of calculating distances in astronomy that work at different distances. In the case of these yellow balls, they are associated with these molecular clouds that have a lot of spectral lines coming from molecules like carbon monoxide. And we use what are called kinematic distances to derive distances from the velocities of spectral lines. So this is a little illustration with the sun, the galactic center here, that shows how this works. So as everything orbits, different orbits around the center of the galaxy at different velocities, we can use models we have of galactic rotation along with the Doppler shift of spectral lines to associate a molecular line and a yellow ball with a position in the galaxy. So this is a little bit complex. If you're not absorbing all of this right now, don't worry. It takes a little bit of wrapping your mind around this to see how this works. But we don't just use these kinematic distances. We have other information that we plug into this distance calculator that gives us the best possible distances we can come up with for these objects. Now, towards the inner galaxy, you'll notice, so this, I don't know how well people in the back can see, but these are labeled, the spectral lines are labeled 1, 2, 3, 4, and 5, corresponding to different places in the galaxy. 1 and 2, you observe the same Doppler shift velocity for things that are close to us on this side of our galaxy and things that are on the far side of the galaxy. So there is ambiguity there, and that's where we use other information we have to sort out whether we're at the near or the far galactic distance. In some cases, too, there are several bright spectral lines. So which velocity do you use to get a distance? Well, in our case, we know that yellow balls are associated with dense gas. So we use molecules that specifically trace dense gas, like ammonia and like OH masers, that are only going to be found near where stars are forming. So we resolve the ambiguity in that manner. And we get the best distances we can. Now, the good news is this worked for about 493 out of the 518 YBs in our pilot region. And we currently have an incredibly talented graduate student working with my colleague Charles at Iowa State University, Nick LaRose, who's working on calculating distances to the remainder of the catalog. And we expect that this will work for at least 70% of the YBs. And we also expect that at that point in time, we will have about 300 relatively nearby objects. Now, 2 kiloparsecs is 6,000 light years. So that's not nearby compared to nearby stars. However, that's actually an important distance, as you'll see towards the end of my talk, because that will allow us to do some pretty cool things. Whereas right now we only have about 30 yellow balls that are at distances less than 2 kiloparsecs. So, So what you're seeing here also takes a little bit of explaining. These are evolutionary diagrams of how protoclusters of different masses along the x-axis evolve as they first gain mass by accreting gas onto stars. That's the vertical lines that are going up here. And then the horizontal lines are kind of like clearing house when the most massive stars kind of like blow away the gas and dust. So these two diagonal lines, things between those two diagonal lines are in the prenatal stage, are in the building up mass stage. These dashed lines, I don't know how well you can see them, those are isochrones. Those link objects at different masses at the same age. So in principle, if we fill this out with a lot of objects, we have a lot of information about where these objects are in the evolutionary stages. The top two panels are yellow balls that are associated with massive star formation traces. And they fall kind of near the knee here. They fall towards the upper line. But there are a lot of much younger objects we've also discovered that fall between these two lines. Underneath the bottom line, that's where you don't really have a protostar yet. That's where the cores have not started to form stars yet. So we're pretty excited about this because it shows that we have protoclusters over an enormous range of mass and luminosity. And again, these tracks are not for single stars, but for clusters of stars. A 10,000 solar mass star would be a pretty whopping big star. So these are actually the masses of the clouds that are forming these stars. Another way to look at the physical properties of YBs is this really useful radar plot. I don't know if anybody has seen something like this before. If you have Keynote on your computer like I do, you can make all sorts of these radar plots. And this is a cool way of plotting 5 different axes rather than 2 or 3. And in this case, these axes all measure quantities that are distance independent. Temperature, surface density of gas. And what's cool here is you can see how different types of objects fall in different parameter spaces. So for example, H2 regions, the pentagons here, the vertices indicate the average measure of that parameter for that particular object. So for example, temperature of the average H2 region, bolometric temperature, 51 Kelvin. Now, the yellow balls occupy a part of the parameter space here that are much closer to the protostars than the H2 regions. So the basic takeaway of a plot like this is the same as the evolutionary diagram. Most YBs are tracing actively accreting, that is, protoclusters that are building up mass. The stars are still growing. They're prenatal stars. And they were missed by a lot of the surveys, the previous surveys, for massive stars. So we're going to be able to do a lot when we have the full survey. So for example, when we have crowdsourced our photometry and we have infrared fluxes, multiple measurements, we are going to be able to explore color differences by age, by mass, by luminosity. This is just a really quick glimpse into some of the things we can do. In this color plot, we're plotting only those protoclusters that have about over 700 solar masses of material in those clouds. And you can see that there's a trend going from the lower right to the lower right to the upper left. The youngest objects are down here, and the oldest objects are up there. And this makes sense because the younger objects are cooler, and there's a temperature difference in going from these young, less luminous regions up to the more luminous regions. So we'll be able to explore how these infrared colors can help us predict things like mass and luminosity and age. And we're using various different techniques to do that, including we're working with an expert in machine learning at PSI who's going to, with her, we're going to explore whether we can actually use machine algorithms to predict YB properties just from the colors alone. So we need a lot more measurements before we can do this, and we're hoping to get that over the next several months. So where do these YBs actually form? I mentioned the Herschel Space Observatory has identified these hub filament systems across the galaxy as these birthplaces of stars. And these filaments can be hundreds of parsecs long, but only like a light year or so across. So they're very, very long, skinny things. So the current paradigm we have for where stars, different kinds of stars form, is that low mass stars actually form along these thin strings, along these filaments. And these filaments come together in these hubs where there's a lot more material, and you can have your massive stars forming in these hubs. So now our graduate student, Nick LaRose, is working on figuring out where in these hub filament systems these YBs lie across the galaxy, now that we have, or we're in the process of getting good distances to the majority of the catalog. So on the right here is this god-awful spidery looking diagram is an illustration that shows how we think stars form, the stellar embryos build up within these larger hubs, within these larger cores that we see at lower resolution from radio telescopes. But using instruments like the JWST, the Atacama Large Millimeter Array in Chile, and the VLA, we can actually probe down to the scale to see how these protostars, how these embryos grow within these cores. And this is where that magic number of 2 kiloparsecs comes in. At 2 kiloparsecs, with the kind of resolution you get, now 2 arc seconds might not seem like great resolution to optical astronomers, but in the infrared and using radio telescopes, it's darn good, it's hella good with the Atacama Large Millimeter Array. At that kind of resolution, you can get down to scales of a couple of hundredths of a parsec, and we can actually measure the way these protostars grow. So towards the end of this project, we are going to be identifying a list of nearby Yellowballs to propose to these facilities so we can compare how these stellar embryos grow in star-forming regions of different mass. So we're really excited about that. So the anticipated results for the full 300 square degree survey are, we're going to have this great catalog, over 6,000 YBs across the Milky Way, with infrared fluxes, with errors, with associations with objects in other catalogs, and with distances and sizes for conservatively, I would say 70%. We might even do better than that. We expect that a few thousand of these yellow balls are associated with modest protoclusters containing stars that are less than 8 solar masses, which would increase the number of known star-forming regions in that mass range by nearly 2 orders of magnitude. And we're hoping that our color analysis will provide a way to sort of place YBs on a color diagram and to be able to infer important things about the age, mass, and luminosity from the colors alone. We will have a generous sample of objects that are nearby in order to probe with these state-of-the-art instruments. So towards the end of this project, we're going to be writing a lot of proposals for ALMA and the JWST. So the timeline for all of this, we have our NSF grant for 2 years, and we expect to launch Periscope to enable introductory astronomy students and potentially others to participate in this research with us by early to, let's say, spring of next year. And I might also mention, if any of you are or know astronomy teachers, not necessarily at the college level, the activities we have, high school students who are taking astronomy could participate in this project as well. So I encourage you, even if you don't think you'd become involved, to take a business card, to leave your contact information so I can let you know when we're ready for prime time. We do intend to publish our first paper, the first data release by summer, but we're going to be updating this catalog for probably at least a few years to come. So we're going to be getting better and better results as time goes by. By this time next year, we're going to have properties, physical properties for most of these YBs, and hopefully the color analysis will have given us some insights into objects that we want to study further at very, very high resolution. And then by early mid-2025, we intend to make this photometry tool available to the astronomy community at large through GitHub and the Astrophysics Source Code Library, together with a guide for adapting it for use on any projects that require measuring the flux from an extended source that's embedded in a nasty background. Because we're using this for Yellowballs, this could be used in a variety of other ways. So that's what I have. And I will stop there and take questions. I know it's probably been a lot to absorb over the past hour. And yes, question there in the back.
Yeah, so have you found that these yellow balls are never found like in a globular cluster? Because those are typically older stars that are pretty well established.
Right, exactly. So these are from, well, first of all, the surveys that were done with Spitzer for these objects were done near the galactic plane in the first place. But these are all associated with young stars and what young stars do to their environment. So the globular cluster stars are old and present a very, very different appearance.
Would they be more full of like really largely dispersed H2 regions since they're so old?
Yeah. So they wouldn't be full of gas, so to speak. The objects that we observe are very clearly still embedded in their birth clouds. And that one thing I skipped over because I know I put a lot of if you followed most of that, pat yourself on the back because I've got figures in here from our 2021 paper for the Astrophysical Journal. And I skipped that one of the things that we showed on one of those color plots is that around these more modest stars, these what we call intermediate star-forming regions, the environments are cooler and there's less ultraviolet radiation. And that has a very distinct color appearance that's different from the really massive stars, from the massive stars that do excite these, what we call the H2 regions. You know, again, astronomy nomenclature, there's H2 for ionized hydrogen, and then there's H2 for molecular hydrogen. But that's with the subscript 2 rather than the Roman numeral 2. Some of the nomenclature here is terrible, and the classification of young stellar objects is terrible, but we're kind of stuck with that. But hopefully we won't be stuck with the name yellow ball forever because that's particularly confusing.
I have another question.
Sure.
Okay. Actually, two more questions. Is this still Herschel only, or also Spitzer and other?
So that's a great question. So that's something else that I didn't. We're using Spitzer and Herschel data. In principle, we could expand and do photometry at other wavelengths. Herschel has a catalog of a lot of these yellow balls are actually embedded in clumps that the Herschel catalog has pulled out. So some of the photometry has been done for us, but one of the things that we're adding several wavelengths here, and we're also adding distances, and that's really critical. That's really important, and that's something that is often missing. And without the distances, a lot of these things you can't derive. But the neat thing about the color analysis that we're trying to to make things as model independent as possible. How much can we actually infer from direct observables? The fluxes, the colors that we measure, that's a direct observable. When you calculate things like mass and luminosity, all of those things are model dependent. So there are a lot of assumptions that go in there. But if we have very good parameters for some of these things that are well studied, and we see these trends, then we can start to actually place objects in color space and infer properties just from the colors alone, if that makes sense.
And my last question was,
Yeah.
these new free-floating worlds that they found in the Orion Nebula, would those possibly show up as with Yellowballs?
Oh, actually, if you're talking about like free floating planets, no, they wouldn't be bright enough. And this yellow ball signature is, this was kind of a beautiful piece of serendipity. A priori, we didn't think about that these photo dissociation regions would be so prominent. And it has to do with the fact that these yellow balls are similarly bright at 8 microns and 24 microns that trace the gas and dust. So they pop out at these photo dissociation regions really pop out at these wavelengths. And the fact that Spitzer was very sensitive enabled us to actually catalog a bunch of pretty low luminosity objects. And that happened only after we specifically asked people to find these for us in the Spitzer images. So we owe a lot of thanks to the citizen scientists that identified these objects, because now we have a fantastic database that we're hoping will tell us a lot about, how do you form regions like the Orion Nebula versus regions that don't contain those stars. Yes?
Well, it seems your work is going to really redefine stellar evolution in the HR diagram. I had two questions. You mentioned M stars are around 77% of the stars, and the other two are maybe a couple percent. It didn't add up to 100%. I was kind of wondering where the other stars are.
Well, so the other stars are like F, A, and G, like solar type stars. So I mentioned that the high and intermediate mass stars together are add up to about 1% of all stars. But then those low mass stars that are 2 solar masses and below comprise the other 99%. It's just that the M stars are the most abundant. Those are the stars that are about 76% or so of the main sequence stars are M stars. Low mass, cool, and they're fairly easy to observe planets around. So a lot of the statistics we have right now, we know of a lot of planets orbiting in the possible habitable zone of M stars. We're still building up statistics on planets around solar type stars like our star.
You mentioned that the filaments, they're pretty the size of the filaments. Do they change as you go further out in the universe, or are they a result of expansion of the universe?
That's actually a great question. So what's really interesting is that nature repeats the same sort of shapes on many, many different scales. And just as we see these hub filament networks in star-forming regions in our galaxy and at lower resolution when we observe external galaxies beyond our galaxy, the models of how structure developed in the universe, galaxies are sort of strung out in kind of filamentary structures with like clusters and superclusters of galaxies at what you could call hubs. If you've seen some models of the evolution of the universe, where there's gravity, a lot of these structures seem to form. But it's also, there's this joke in astronomy, consider a spherical cow. We used to think about these clouds as everything being nice and spherical and, really tidy, and they're not. I mean, filaments are not spherical. There are cores that are more or less spherical in the filaments, but But that's a great question because we see structures like that. Just like I didn't talk about the stages of low mass star formation, I just wanted to show you what the stages look like. These bipolar outflows you get from protostars, you might have noticed them on that one illustration. You get those kind of flows from the centers of galaxies. So outflows are also a general feature of where you have something that's shaped more like a disk around an object. You get these outflows. So like the physics is a little bit different, but it's also similar on very very different scales.
One last question.
Yeah.
You said you had the PDR. You get if it's a really high intense region, you get a lot of hydrogen alpha. Is that just due to the ionization of the hydrogen, or just blowing gas away that you can see the H2 regions?
So two different things. First of all, a PDR photodissociation region, that's just where molecules are dissociated near various different types of stars. An H2 region is formed by the most massive luminous stars that have the ability to ionize gas around them for parsecs sometimes around. And these things do expand the radiation and winds from these stars, so they get bigger in time. So for example, the Orion Nebula is what we call a diffuse H2 region. It's about 3 million years old. Some of these younger H2 regions are a little bit more circular, a little bit more compact. But in time, these things do expand, and these stars do dispel the gas. And that's why, we think that our sun formed in the proximity of massive stars, but all of that disbanded a long time ago. That plus the fact that orbits around the center of our galaxy are differential. The Milky Way doesn't rotate like a pinwheel, like a solid body. So these orbits stretch out in time, and whatever siblings the sun was born with have, left the nest, so to speak, and wound up in different parts of the galaxy. Because one orbit at the position of the sun, one orbit around the center of the galaxy is something like 275 or so million years, which is actually fairly sure the sun has made its way around several times since its birth. The sun's about 4.5 billion years old now, and it's going to be stable for a while, fortunately for us.
Thank you.
Sure, thank you. Yes?
So I have a question, if I understood it correctly. So the yellow balls are sort of like the Orion Nebula, but they contain less gas, so they're going to form stars that will not be as massive as some of the stars in the Orion Nebula?
Yes, most of them are like that. There are some that will form massive stars, but most of them are forming more modest stars. They're associated with less gas than the amount of gas that was in the Orion Nebula.
And then the end product of evolution for this yellow ball will be then a star cluster, correct?
It will be a star cluster, yes. And star clusters, whether they stay bound or not, depends upon various things like how the gas is dispelled, how old they are, and really, again, it's kind of exciting because, we talk about star clusters, we also talk about star groups, which, a cluster like Orion contains thousands of young stars, but some of these groups maybe are forming a few dozen stars. So a lot of this is actually exploring new territory, so we're really excited about this. And we're happy that NASA and NSF were apparently excited by what we were doing too. Especially now that I'm dependent on grants for my salary, I'm really excited to have grant funding. Yes?
In looking for volunteers to contribute, now is that just like PC work, or is there other stuff? What would they be doing?
Right, so this is an excellent question. In looking for volunteers, we are specifically looking for people that will help us do the photometry. What we did for our 2021 paper is we had 6 independent measurements at each wavelength of each source. So it wasn't just me doing photometry, it was my colleagues, it was some students, and by putting all those measurements together, I mean, we could estimate the errors. Like, some of these things are really hard to measure, and you just don't trust the photometry because what one person measures looks very different from what somebody else measures. So we estimate errors by, basically having a lot of different measurements. Similar to, what you might do in an experiment in a high school physics class, where you're making many different measurements and you're adding them up to see what the standard deviation of all those measurements is. So yes, in particular that, we're looking for help in visually going through these images to also say something about the reliability, to be able to flag different images, like, if there's a flaw in the image, if it's coming up looking like something that's really weird or not a YB. In some cases, there are some just plain stars thrown in there. So we're, like with a project on Zooniverse, you can sort of get involved to the extent that you want to be. I mean, there are some people who've participated in Zooniverse projects who wound up co-authors on papers because they've really gotten into that. We have not yet decided what we are, like how many measurements. I mean, clearly we wouldn't be asking everybody to, do 6,000 times 4 measurements on all of these objects. People would be working with a subset of the database, and then it's going to be our job to sort of combine all those measurements and do the statistics and everything. But yeah, we're looking for primarily help in the photometry and maybe visual inspection. My colleagues and I would have to decide a reward system based on what people could give us. And by reward system, I don't mean monetary compensation. There's no money for that. But it's certainly acknowledgement on papers. As I said, co-authorship is not necessarily off the table. People to be involved in maybe even press releases or media interviews. For younger people, maybe you add to your resume that you were involved in a research project. This is kind of a project, so there are these things called CURES, C-U-R-E-S, stands for Course-Based Undergraduate Research Experience. And that's sort of what this is. This is at a level of complexity that's higher than what you find on Zooniverse, but not so high that we need advanced graduate students or even advanced undergraduates to become involved. This is a project that can be done with just a little bit of background on learning about the background astronomy and learning how to use the tool. People who help us won't actually be doing coding. They'll be using the tool to help us with measuring the emission from these yellow balls. Thank you. Yes, back there.
So I guess I'm surprised. I fully expected to hear you tell us that you had built a learning model for this, or trained a model to recognize yellow balls and stuff. And the fact that you haven't must mean that there's some advantage to using students. Is it just this?
Yeah, so there are some things, and and this is characteristic of citizen science in general. There are some things that you just can't use machines to replace humans with yet. Humans are very good at identifying patterns. These objects, again, they're complex. They're not all beautifully round. They're embedded in very complex backgrounds. And we need the visual inspections. The machine learning can come later. I mean, that's the beautiful thing about citizen science. Some visual identifications by humans are being used to train machines to become better at picking out patterns. But for what we're doing here right now, we need human beings. We need the human interface with making decisions. That little video that I showed you was an example that just ran through a couple of examples quickly. But for instance, we need the human eye to basically judge when they mark off the yellow ball, when the code has run through and given you the result, to say, that's a good result, I'll keep that. You can also choose to redo it. So this is, this is something that a machine would not, at this point, be able to do.
Seems subjective.
Somewhere down the line, there is a certain amount of subjectivity, but that's where crowdsourcing comes in. And Zooniverse has time and time again showed that the wisdom of the crowd is pretty darn impressive. People do a really good job at spotting patterns. I mean, it's like, with things like the animal identification projects on Zooniverse, computers are still pretty lousy at distinguishing between, say, a goat and a sheep or something like that. There are just, and I don't know if you've played with chatbot or not, but that's come up with, with some, AI sometimes come up with some really, really weird results. So that's a work in progress. But we are exploring using machine learning techniques to sort of see how these things sort and to maybe come up with models for identifying YBs by their properties. Yeah.
Why do you think? Why would you think people would be opposed to installing Python in their computers?
Oh, I don't necessarily think they would be opposed to installing Python, but the point is you don't need to have Python installed if you're going to use like a Colab or something on the internet. I'm perfectly happy to have people install Python, and when we're ready to go to run our code, because our code also uses fairly large mosaics from the Spitzer Space Telescope that get chopped up for these individual images. So one of the things we're addressing right now is the space program. The space program, meaning the fact that this takes a lot of memory, a lot of computer space when you're doing a classroom activity with everybody running this at the same time. We're working on those issues. We'll have them straightened out very shortly. Yes, over there.
How many data points are you talking about with it? Like for a machine learning model, how many data points would you have?
Well, so that's a great question. And we're starting with, we're looking at how many, for example, different infrared fluxes we need for machines to reliably predict things like, this object has this luminosity or this mass or this gas surface density. We're looking to predict especially the distance independent parameters that will tell us something interesting about the youth of these objects. So we're exploring various techniques. I am not an expert on machine learning by any stretch of the imagination. And that's why astronomy involves collaborations. And this woman that we're working with at PSI, down the line, we're still several months away from being able to explore this. We're going to be working with somebody who is an expert who will help us with predicting some of these parameters based on her machine learning models. Anybody else?